If you've ever stared at a textbook the night before a math exam, surrounded by dozens of scattered sine and cosine formulas, you know that specific kind of panic. The standard way we're taught to handle this is brute force. We make flashcards, write equations out 50 times, and try to drill a massive list of rules into our heads. But treating trigonometry like a giant memory test is exactly why the subject feels so difficult. Every single identity on your curriculum can actually be built from scratch using just two basic geometric shapes. Developing a mastery of visual translation, where every formula corresponds to a physical location, is what makes these equations impossible to forget. We start with a clean slate and a single rule. Draw a circle with a radius of exactly 1. This diagram shows our unit circle. Drawing a radius line out to the edge, then dropping a dashed line down to the axis, traps a right-angled triangle. That horizontal base is exactly cosine, the x-coordinate. And the vertical height is sine, the y-coordinate. By placing this one triangle inside this one circle, the abstract words sine and cosine become physical distances you can measure with a ruler. Look closely at the diagram we just built. If we take the Pythagorean theorem from middle school, where you square the two sides to equal the hypotenuse squared, and apply it here, our base squared plus our height squared equals 1 squared. That gives us sine squared plus cosine squared equals 1. Without doing complex algebra, we generated the single most famous identity in trigonometry. You don't need to memorize the other two. Dividing our starting equation by cosine squared immediately simplifies it into 1 plus tangent squared equals secant squared. And if you divide that exact same starting equation by sine squared instead, you get the third identity, 1 plus cotangent squared equals cosecant squared. Knowing the geometry of that single triangle completely replaces the need to memorize 3 separate foundational formulas. That same logic applies to the sum and difference equations, which consistently cause the most errors on exams. These identities follow a rigid linguistic logic based on the behavior of the plus and minus signs. This graphic shows the sum and difference formulas. Expanding a sine equation always carries the exact same sign into the middle. A plus stays a plus. But for the cosine formulas below, the sign strictly swaps to its opposite. These predictable sign behaviors are the building blocks for more advanced formulas, like sum to product, because they dictate how terms either merge together or cancel out. This visual approach also clears up one of the most confusing parts of the curriculum: why solving a complex trig equation gives you an infinite number of answers, usually attached to the letter n. Watch this diagram of our rotating radius. As the line sweeps around the circle, it logs a marker at a specific angle. But if the line keeps spinning and completes a full rotation of 2 pi, it hits that exact same physical spot again, and again at 4 pi. Because a circle is a continuous, endless loop, that rotating line has no choice but to strike the same coordinates over and over. The variable n functions as a physical lap counter, tracking how many times you have completed a full circuit around the circle. Infinite solutions don't happen because the math is ambiguous. They happen because a spinning circle never stops. This graphic shows a high-level, official board exam question. We have to prove that this long string of sines and cosines equals 0. By identifying the sign-matching behaviors we saw earlier, we can use sum to product rules to collapse these intimidating additions into simple multiplications. Once expanded, the terms in the first half of the equation mirror the terms in the second half. Because the signs follow our predictive patterns, they inevitably cancel each other out to equal 0. Every step of this proof relies on the structural ladder we just built. The circle provides our coordinates, the triangle provides our core identities, and the signs provide the patterns. When you stop trying to memorize mathematical symbols and start visualizing the geometry behind them, you will arrive at the right answer every single time.